Hello, everybody. This lesson is on section 10.10 in your calculus text on applications of Taylor series. So we've been looking at ways that you can create Taylor and Maclaurin series for functions. And so for the first couple examples, we're going to try to recognize a pattern when we have 1 plus x raised to some power m, in this case 5 halves. And then as soon as we recognize that pattern, we're able to apply it to any exponent. And so if we start creating this Maclaurin series from scratch, we would need, let's see, f of x is equal to 1 plus x raised to the 5 halves power. So f of 0 is 1. And then f prime of x would be 5 halves, 1 plus x to the 3 halves power. So f prime of 0 is 5 halves. F double prime of x is 15 fourths. 1 plus x to the 1/2 power. So f prime of x, f double prime of x at 0 is 15 fourths. The third derivative is 15 eighths. 1 plus x to the negative 1/2. If we plug in 0, we get 15 eighths. And so I was simplifying these coefficients in front as we went each step, but recognize that this first one is 5 halves. This one is 5 halves times 3 halves. We got that when we did the derivative. We had the 5 halves here originally, and then we brought the 3 halves in front. So we have 5 halves times 3 halves. This one is 5 halves times 3 halves times 1/2. That's going to be important to recognize this pattern. So this is our exponent, 5 halves. And then we have that same exponent, 5 halves times 1 less than that. And then we have the same number, 5 halves, one number less than that, and one number less than that. And so that pattern will continue forever. And so if we go ahead and do one more, the fourth derivative is going to be 5 halves times 3 halves times 1/2 times negative 1/2. 1 plus x to the negative 3 halves. And so then the fourth derivative at 0 is 5 halves times 3 halves times 1/2 times negative 1/2. And again, we see our original exponent, that exponent minus 1, that exponent minus 2, and that exponent minus 3. And so now we have enough to write out the Maclaurin series. We can say 1 plus x to the 5 halves is equal to f of 0, which is 1, plus 5 halves times x, and then 5 halves times 3 halves x squared, plus 5 halves times 3 halves times 1/2 x cubed, 5 halves times 3 halves times 1/2 times negative 1/2 x to the 4th, and so on, going on forever. So of course we could simplify that, but by simplifying we don't see the pattern that we were looking for with the coefficients. So simplified, it would look like this: 15 fourths x squared and 15 eighths x cubed and negative 15 sixteenths x to the 4th, and so on and so on. So the pattern that we recognized there is written here as the binomial series. So anytime we have the quantity 1 plus x raised to any power m, then we can write that as 1 plus this sum. And this sum is basically what we got here. And so this notation, m choose k, when it's m choose 1, you're just going to get m. M choose 2 is going to be m times one number less than that. And then for any number bigger than 2, it's going to follow that same pattern. Our exponent, remember our exponent is m, so m minus 1, m minus 2, m minus 3, and so on. And it's going to have the same number of terms as k. So when k is 1, we get 1 term. When k is 2, we get 2 terms. When k is 3, we have 3 numbers multiplied on the top. When k is 4, we have 4 numbers multiplied on the top, and so on and so on. And so we will use this binomial series theorem to do example 2. And so according to this theorem, 1 plus x to the 1/3 should be equal to, looking here, we have 1 plus this sum. So that's going to be the sum from k equals 1. We're looking for the first 4 terms. We already have 1 term here, so we only need 3 terms from the summation. And then it's going to be m, which is 1/3. Choose k, x to the k. And so now if we expand that, we're going to plug in k equals 1. And so that's going to be 1/3 choose 1, x to the first power. When we simplify that, as it says here, m choose 1 is just m. So this is going to be 1/3 x to the first power. And then when we do k equals 2, we're going to have 1/3 choose 2, x to the second power. And so that is 1/3. And then 1/3 minus 1 is negative 2/3. So notice there are, when k equals 2, we have 2 numbers in our product. And that's going to be over 2 factorial from this. And then we're going to have, when k equals 3, we're going to have 1/3 choose 3, x cubed. And so that's going to be 1/3 times one number less than that, negative 2/3. M minus 2 is going to be negative 5/3 x cubed. And again, since k is 3, we have 3 numbers in our product on top, and then it's going to be divided by 3 factorial. And so then our final answer is going to be 1 plus 1/3 x minus 1/9 x squared. Here we're going to have 10 over, let's see, we have 3 times 3 times 3 in the denominator and also 3 factorial. So that's 27 times 3 factorial, 27 times 6. Is 162 x to the third power, which could also be written as this. So that's our expansion using the binomial series expansion. So we did the first example with the power being 5/3, or sorry, 5/2. And then we did the second example using m equals 3/2. Another application of Taylor series is using Taylor series to evaluate integrals that might be otherwise difficult to evaluate. So for example, finding the antiderivative of cosine of x squared is not easy to find the antiderivative for cosine of x squared. So if we use a Taylor series to represent this, we know the series for cosine is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. So we know that from previous lessons and from our table of common Maclaurin series. And so if we want the cosine of x squared, all we have to do is replace all the x's with x squared. So that's 1 minus x squared squared over 2 factorial plus x squared to the 4th over 4 factorial minus x squared to the 6th over 6 factorial, and so on, which would be 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial minus x to the 12th over 6 factorial, and so on and so on. And so now we can evaluate this integral by finding the integral of that infinite series. And so the integral of cosine x squared is equal to the integral of 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial minus x to the 12th over 6 factorial. I'm also going to include the general term for the Maclaurin series. For cosine x, the general term is negative 1 to the n plus 1, x to the 2n over 2n factorial. This is actually negative 1 to the n. And so then here, it's going to be negative 1 to the n, x squared to the 2n. Here, I'll squeeze it in here as well. Negative 1 to the n, x squared to the 2n over 2n factorial. And then in this case, so it's going to be x to the 4n over 2n factorial. And so if we put that in here, then we'll be able to integrate the general term as well. So this series goes on forever. So if we integrate term by term, the antiderivative of 1 is just x. The antiderivative of x to the 4th is x to the 5th over 5. So we're going to have negative x to the 5th over 5 times 2 factorial. And then this one is going to be x to the 9th over 9 times 4 factorial minus x to the 13th divided by 13 times 6 factorial, and so on and so on. So if we do the same thing to the general term, we're going to increase the power by 1, so that's 4n plus 1 divided by 4n plus 1 times 2n factorial, and so on, plus any constant. So that is our antiderivative of cosine of x squared written as an infinite series. So now we're going to use that result for example 4 if we want to evaluate this integral. In example 4, it was an indefinite integral. There were no endpoints, but here we have endpoints 0 and 1. So we could evaluate this as an infinite series. So the integral from 0 to 1 of cosine of x squared dx, our antiderivative is x minus x to the 5th over 5 times 2 factorial plus x to the 9th over 9 times 4 factorial minus x to the 13th over 13 times 6 factorial, and so on and so on. In general, it looks like this. And now we're going to evaluate that antiderivative at its endpoints 0 and 1. So when we plug in 1, we get 1 minus 1 over 5 times 2 factorial plus 1 over 9 times 4 factorial minus 1 over 13 times 6 factorial, and so on and so on. It's going to be negative 1 to the n. 1 over 4n plus 1 times 2n factorial. And when we plug in 0, all the terms are going to become 0, so then it's minus 0. And so we want to estimate this with an error less than 0.0001. So this is an alternating series. And remember back in, I believe it was section 10.6, we learned the alternating series truncation error is no larger than the next term. So we want to just keep going until we have a term that is smaller than 0.0001. And so if we set up a table where n is the number of terms, and the nth term we'll start with this would be considered the 0th term. So when n is 0, the value of our nth term is 1, looking here. And when n is 1, that puts us here. That is 1/10. We're taking the absolute value. And here, when n is 2, we get 9 times 4 factorial. So that's 9 times 24, which is 216. So 1 over 216. As a decimal, 1 divided by 216 is about 0.0046. So it's not small enough yet. So we'll go again. When n is 3, that would be this one. So 1 divided by 13 times 6 factorial. So 1 divided by 13 times 6 factorial. That is 1.068 times 10 to the negative 4th. One divided by 13 times 6 factorial, we said is about 0.001068. And so that is not quite small enough. Looks like we're going to need to go one more. So now it's going to be 1 divided by, when n is 4, then this number in the bottom, 4n plus 1, that's 17, times 2n factorial, so that's 8 factorial. And that is about 0.000015, which is definitely less than the error that we're looking for, 0.0001. And so if we go to the if we go to the n equals 3, the next term, our error is smaller than our next term, which is going to be smaller than 0.00001. And so our estimate, we can say the integral from 0 to 1 of cosine of x squared dx is approximately 1 minus 1 over 5 halves plus 1 over 9 times 4 factorial minus 1 over 13 times 6 factorial. So this was 0, n equals 0, n equals 1, n equals 2, n equals 3. And so if we want to n equals 4, our next term would be 1 over 17 times 8 factorial. That term is small enough so if we truncate here, our error is smaller than that value, and that's what we want. So we're just taking this part, and so if we type all that into our calculator, that's going to be 1 minus 1 over 10 plus 1 divided by 216 minus 1 divided by 13 times 6 factorial. And that is about 0.9045. .227. 228. Okay, so that answer we know is at least accurate to the thousandths place because our error is smaller than 1/10,000th. We can also see how close that answer is to the actual value if we did the integral using Math 9, the integral from 0 to 1 of cosine of x squared with respect to x. That integral, the calculator says, is 0.90452, and that is very close to the answer that we got by using only the first 4 terms. Okay, for this last example, we can do the same thing that we just did with the integral to evaluate a limit. And so what you're going to do is use the Maclaurin series for e to the x and the Maclaurin series for e to the negative x. Expand each of those and then combine any like terms that you have, and then see if you can evaluate this limit directly using that series. So go ahead and pause your video, try out example 5, and then press play when you're ready to compare your answer. Okay, so the Maclaurin series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on and so on. It's x to the n over n factorial in general. The Maclaurin series for e to the negative x is the same series, but we just replace all the x's with negative x. So that's going to be minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial minus x to the 5th over 5 factorial, and so on and so on. So it's negative 1 to the n, x to the n over n factorial in general. And so that means we're taking the limit as x approaches infinity of e to the x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on, minus e to the negative x, which we said is 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on and so on. And then we're going to divide by x. Okay, so if we go ahead and subtract these two expressions, 1 minus 1 is 0. X minus negative x, x minus negative x is minus x becomes plus x, so that's going to be 2x. So we have the limit as x approaches infinity, we have 2x, and then this term and this term cancel because we're subtracting, and then this term and this term together would become 2x cubed over 3 factorial, and then this term and this term would cancel. The next term would be plus 2x to the 5th over 5 factorial, and so on. So what we see is the even powered terms are all subtracting away and becoming 0. The odd powered terms are doubling up. And so in general, this is going to be 2x to the odd power. So an odd power would be 2n plus 1 over 2n plus 1 factorial. So we use 2n plus 1 because that'll create any odd power starting with n equals 0 to get the first term that we have. And now that's all divided by x. And so if we divide all those terms by x, that becomes 2x plus 2x squared over 3 factorial plus 2x to the 4th over 5 factorial, and so on. That's 2x to the 2n over 2n plus 1 factorial. Or 2, yeah, that's right. And then as x approaches infinity, sorry, x is not approaching infinity, x is approaching 0 for all of these. X is approaching 0. And so, sorry, this first term when we divide by x just becomes 2. And so, because we're doing 2x divided by x, that would be 2. And then we divided this term by x, and we got 2x squared over 3 factorial. And so as x approaches 0, this term approaches 0, this term approaches 0. All these terms are still going to have x's, are going to approach 0. And so we're just simply left with 2. So this limit is equal to 2. And that completes our notes for section 10.10, and that is the last section in chapter 10. So here are some good practice problems that I've selected from 10.10. Please try those, at least a few of them, and let me know if you need help on any. Take care. Have a great day.